Hello, everyone. Welcome back. It's 10 past. I'll start the lecture. Just a few logistics before starting. I think you're all familiar with this. I just wanted to say that the posted slides, I have made a few changes. There's some typos, and I added in one slide. I'll post updated slides at the end of this lecture. The changes aren't much. I'm just going to go over. Actually, I'll do a quick review of where we dropped off last week and start from there. So I think we talked about trigram models. We introduced trigram models as a pedagogical language model, a simple language model. And then we looked at some of the bottlenecks and ways to circumvent that problem, like we looked at negative sampling and hierarchical softmax. I added a slide, I think slide number 46. So I think Sean talked about perplexity in lecture 2 or 3, am I right? Yeah, so he already covered it. So I alluded to it, but I thought I would add a specific slide after 45, which is, when we're doing the backpropagation, the cross entropy loss. So I explicitly tied how perplexity is the common evaluation metric that you'll see in language model evaluation. And I just tie in how perplexity ties with cross entropy loss. So we looked at hierarchical softmax with grouping, and then we'll start talking about more regular language models today. We'll talk about recurrent neural networks. And before we get started, I just wanted to give you a sort of intuition and the problem formulation that why do we want to use recurrent neural networks. So when statistical language models, you've looked into n-gram models, you're familiar with bigram and trigrams are. But if we want to formulate a language model using, let's say, bigrams and trigrams, one of the problems is the obvious computational burden, because there's going to be a lot of bigram or this n-gram combinations which are not feasible computationally. And secondly, this is based on a Markov assumption that the next word is dependent on a short linear history of previous words. If we want to expand on that, so let's say instead of just on the previous word, we want to look at like all the previous words in a sentence that we've looked at. Can we do better? So the RNN intuition is for ameliorating the computational burden is to use recurrence relationship. So use one set of weights, and then we have a recurrent connection so that we remember the previous words using that recurrence connection. So to show this pictorially, on the right-hand side, you can see a rolled-up representation of an RNN, and on the left-hand side is like a slice with the computational graph. So going in the subsequent slides, you'll see I will usually use unrolled representation of RNN, but this is like a rolled up representation just for illustration. And on the left-hand side, the way it works is that if you take, let's say, if you have input X and you have a hidden unit output, and then that's you have some it's a supervised learning setting, you have a ground truth, and then you calculate some kind of loss, and you backpropagate that loss to update these weights. So there's a question last class, actually both sections, that what about this weight matrices? Why are there 3, or why can't we just use one weight matrix instead of like HH and HX? As you'll see that this is mostly for better pedagogy. You can use it, you can combine them together, and it doesn't make any difference. Okay, so this is this is an unrolled representation where you can see each of the inputs unrolled through time. And if you think about it, it's just a 2-layer feed-forward network, right? And the only thing that's different is that we have a recurrence connection, the HT1. So the input at a time step, let's say T1, has an input as the previous hidden state being fed back to it. Apart from that, it's essentially like a 2-layer feed-forward network with one hidden layer and output layer. And yeah, so it's basically the input or output can be anything that you want it to be. So in this case here, you're giving input English words, and the outputs are parts of speech tagging. Okay, so let's take a look at a one-time step snapshot for a better understanding. So let's say we have a list of word vectors for the sentence, two riders, blah, 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 approaching on horses or something. And then let's take a look at time step where we have the word two riders where, and you have the input xt, and you have the previous word ht1 getting fed, and then you have the y hat, which is let's say this is a language modeling task. You're predicting the next word, and yeah, you're basically like calculating your y hat and then back propagating the loss. Now, does everyone see that why these two lines are equivalent notation? So this is the thing I was alluding to in last slide, that you can just combine this weight HH and HX and represent it as an input weight, and use like a concatenated vector of the hidden vector and the word vector is the same thing. Okay. This is all, if it's all too abstract, here's a concrete like code implementation, a very simple RNN, where we're basically like, yeah, you're just doing this in Python using NumPy so that you have a concrete understanding of how it looks like in code. Any questions? Okay, so now how do we form the language model? Again, what have we achieved from doing this? So if we use RNN like this, and if our dimension of our hidden vector is less than our vocabulary size, which obviously it is, our vocabulary could be in the range of like 100,000 words, we've obviously reduced the number of parameters from training an n-gram or previous approaches. This we can, in theory, we can maintain this in an arbitrary length of a sentence by just back propagating through time. We can just like, doesn't matter how long a sentence is. Technically, we're having that information carried through using this recurrence relationship. But in practice, this doesn't work that well because what we call retrograde amnesia, where this catastrophic forgetting is common. So if, for example, if we take this sentence, if you think about a very long sentence, so the teacher taught transformers terribly, telling tiring tortuous theories, let's say. But it's such a long sentence that by the time we get to theories, we have forgotten that whether it was Gerald teaching transformers or me teaching transformers. So that information is lost. So we can, there's like an information bottleneck on the last step where it has to remember all the preceding words through recurrence. And if it's a long sentence, then as we'll see that we can suffer from things like vanishing or exploding gradients and things like that. So the best way to understand or intuitively think about this, why this retrograde amnesia or things like vanishing or exploding gradient happen, is to think of a number that's slightly bigger or less than 1 and raised to the power of t, and then you keep, as you increase t, you can see that the number that is slightly bigger than 1 will explode, and the one slightly lower will just vanish. So that's an intuitive way to think about the problem. So in the next few slides, I'll use this diagram here. Just like A's are identical recurrent cell blocks, and we'll go step by step to what happens inside them. And yeah, so these are the notations. The yellow blocks are neural network layers. It's a pointwise operation, and there's some notations for vector transfer, concatenation, and copy. Okay, so let's go through this block by block. So so the goal here is to address this long time memory problem in RNNs. And we'll go through this architecture called long short-term memory, or LSTMs, which is a very popular form of RNNs, and see how it works to circumvent the long short-term memory. So the main idea, I think, at a high level is that in LSTMs, we maintain information highway or like a connection that goes from start to end. And essentially think of it as like an information highway where you're adding information and removing information at every time step. Okay?
And as the output, like you'll see that, so this information highway will say that as cell state denoted by C, and we'll maintain this C as a recurrence relationship throughout through the entire length of our input. So before we're getting what? So before we're getting like one hidden state output and with a previous hidden step and an input at time step t. So now we're getting like two outputs where one of them is the context or the cell state at that time step, and then we have the hidden state vector ht. And these are again the notations. So one thing about this notation is, for regulating this information flow, we use this things called gates. So the gates are represented by a sigmoid neural network and a pointwise multiplication. Now remember that what did the sigmoid do? The sigmoid squashes values between 0 and 1, right? So if you think, you can also think of this as like from the signal processing field as bandpass filters, but there's a slight difference because filters that way they're always contiguous. But with gating layers, you can block any units or positions in the dimension. So think of it as like a vector mask. So think of like a vector mask with 0, 1 values that essentially allows information to pass through where it's 1 and blocks information where it's 0. So whenever information is coming or you're using this gating layer, so the gating layer, the sigmoid neural network will basically output like a mask, and you'll apply that mask. This multiplication is basically you're applying that mask to whatever the other thing is going through the gate, okay? So in LSTM, in each cell, there are like 4 interacting neural network layers. Out of the 4, there's, see the ones with the sigmoid, they're the gates, and then you also have a hyperbolic tan neural network over here. So don't worry about the whole thing. We'll go about each of this gates or neural networks one by one. Any questions so far? Okay. Okay, so the first step is the so-called forget get layer, where it decides what information we want to forget. So you have the previous hidden state and the input at time t, and that goes through a forget gate, and then that's outputted as ft over here. And this basically what it does is that so this example, by the way, this is for more like explanation. I mean, so you can think of this intuitively that let's say you're trying to decide what should be the conjugate verb for a subject. So he is running or he was running versus they were running, right? So the he and they, for example, so things like that. So so it could be that you have they were running, and then there's a new subject appearing, so you want to forget the previous subject of the sentence, so you decide to forget that. So this is just a example for illustration, but it's neural networks, so it's not that explicit or deterministic like that. But yeah, the role of the forget get is to take in the current input with the previous hidden state, and then output like whatever the forget vector that we want to forget. And then we have the input gate layer, and it has 2 steps. We have sigmoid, like a gating layer, which decides which cells to update, and then we have a hyperbolic tan layer that gives us the new cell state candidate. Okay, and so basically the new cell state candidate, and we're going to push this new cell state onto our previous cell state. Now, what this input gate is doing is that it's applying a mask to tell which values of this new candidate we want to push into our information highway. Does that make sense? So essentially, you have two neural network outputs here. This is the gating output, and then this is the new candidate output from previous hidden state and current input. Yeah.
How is this related to context vectors?
We'll come to that. Yeah. Yes.
Is there any special reason why we need our subjects
Yeah, so for everyone, the question was that, is there a reason why you were using sigmoid sometimes and sometimes hyperbolic tan, and what's the difference? So yeah, so this is what I alluded to earlier. So whenever you see a sigmoid, so you have to think about the activation function, what it's doing. What does the hyperbolic tan do? It's also like sort of normalizing or squashing the output between -1 and 1, right? So it's sort of normalizing the information flow. But the role of the sigmoid is that we want to get a mass vector like 0 or 1, right? So if you think about it, that if we pass through a sigmoid layer, you have some zeros and ones. So and then you multiply that with your -1 to 1, the normalized information, and then basically what it does is it blocks the bits that are at 0 or the units at 0, and then that gives the output. So the role of the sigmoid is to act as a gate. And tan H is just you're normalizing the flow of information. You're not trying to block anything. You have like some information, you're like, okay, I'm going to standardize this and let it go. Okay? All right, so then obviously the next step is to now that we have our new candidate, we want to update our cell state. And so we have our forget what we want. We know what we want to forget. We know what we want to remember or update our memory, and then we basically we add them together. So let's go through this pictorially. Let's say this is our previous cell state, and then you multiply that with the forget gate output, and then just for illustration, let's say your memory gets a little bit shady over this point, and then you want to push new information there. So from your input gate, you have the new candidate cell state, and then you're pushing that information into your information highway or your cell state, and then you have your updated cell state at time t. Okay? So now that we have one of our outputs, like the cell state output, so we also want to look at how what is our hidden state output at ht value at time step t. So for that, we're going to use the output gate. Okay? And here we can see that the output is based on our current step input xt and previous hidden state vector ht minus 1, and we combine the output with the cell to give you, with the cell state information to give the current hidden state vector ht. So if you think about this, this is, you can think of C as the long-term memory and the hidden state at each time step as the short-term memory, and hence the name long and short-term memory. Okay, any questions? Okay, so basically we covered the fundamental building blocks of LSTMs, but obviously there are many different variants and variants to this vanilla structure. So some of the common changes could be that you can have, we have looked at, until now we have looked at unidirectional RNN blocks, but you can actually combine them with bidirectional RNN blocks where you have two layers of RNNs, one doing forward representation and the other one doing backward. So at each time step, you'd have a forward embedding and a backward embedding, and you can concatenate them together. You can also have just unidirectional multiple stacked layers of RNNs. So essentially, yeah, so we'll look at two special cases. And then, yeah, so for example, like in this slide, you can look at two popular variants to the LSTM structure that we just looked at. So if you look at the diagram now, then you can see that what this is doing is that each of the gates, you can identify a gate by the sigmoid layer. And each of the gates is a connection coming from the cell state directly here. So what it does is that over here in each of, so you have a forget gate, you have an input gate and output gate, they have the cell state information at each of the gating neural networks. They call it peepholes that allow all sigmoids to read the cell state. The other one is you can also, for example, in this variant, you can couple the forget and input gates, right? So here, instead of having like input gate, which we saw in a vanilla LSTM, we're just having, we're just merging it with the forget and input gates. So we're doing an interpolation, and we're getting rid of it. So yeah, so you can understand that, like how it's possible to have myriad combinations of this architectural elements to have a different architecture or model. In fact, yeah, another very popular variant is gated recurrent units, or GRUs. And GRUs were popular because they required less parameters and they were like easier to train. And here, some changes that were made was they got rid of the input-output gates altogether. Sorry, they got rid of the cell state altogether, and then you basically have the input at xt at time t, and you have the previous hidden state, and based on that, you're just outputting the hidden state. And you do this by combining the input-output gates into one update gate, and then you have a reset gate, and basically you use an internal like hidden state vector and to output the hidden state vector t at time t. So the obvious question that arises is that out of so many different variants, which one is the best? So there's nothing called the best. Essentially, there's, as I mentioned, that there can be myriad combinations, and it really depends on your evaluation task or what you're trying to achieve with it. And there are many different papers that almost every paper introduces some kind of variance to these architectures. If you are interested, you can read up on these two papers over here that sort of do a nice comparison and survey of different RNN architectures. And basically, essentially, the finding in a nutshell is that they're almost same. Some work better than other, but in general, it depends on the task. Okay. All right, so now we're going to look at contextual word embeddings. So if I ask you the question, what does the word play mean? And I give you two different pictures, the answer will differ broadly. So on the left-hand side, you can see a play at a theater or an orchestra setting, whereas on the right-hand side, you have a soccer match, plausibly between England and Cameroon. And if I show you that picture in that context, play would mean something completely different. So that was the intuition or the main idea in the Elmo paper in 2018 by Peters et al. And this paper had I would say, a huge impact in subsequent papers in the word embeddings or word representation space. So the idea is, instead of we've looked into GloVe and other word2vec like static word embeddings, and this paper introduced like sort of the contextual word representations and their efficacy in downstream NLP tasks. So the idea is using a bidirectional LSTM. So instead of seeing, like, you're going to have access to the entire sentence. So for example, here, again, up until at time step 1, we have the problem of play. We don't know what play it is. So the play, the play was exhausting for the, let's say, and up until the, you don't know whether it's the actors or the soccer players. So, but if you had the entire context from start to end, in that case, you could answer that question or disambiguate the meaning of players better. So the idea is what we have looked at before, that you have like two layers of neural networks, one with forward representation and the other one with, actually you have, like, at any position t, you'd have forward representation and a backward representation. You'd concatenate that representation together with the word token embedding, and then use that for use that for your downstream task or whatever you're doing. So essentially, what happens is that a layer for each token, and let's say you have L layers, you'd have a representation that's 2L plus 1, where the 1 comes from the word token embedding, which is this guy over here, XLM, and then you have a hidden vector representation coming from the forward LSTM, and then you have a backward LSTM representation. You concatenate all this together, and you have L layers, and then you have the preliminary representation, and then you do a task-specific weighting to produce the final embedding for word token K. So for illustration, you can see that here you have the word play, you have the word token embedding for play, X1, and you have a backward, 2 layers of backward embeddings, so all the words that coming from after play, and then you have the forward embeddings. And in step 1, you concatenate, and this is with respect to the time step where you see play. So you have the forward embeddings concatenated with the backward embeddings. You concatenate them, and then you multiply that with some weight of the tasks, weight-specific task, and you sum them all together to get the final embedding. And then you use that task-specific embedding for whatever the task you're evaluating it against. And what that gives you is, and if you use this final embedding, so what that gives you is elucidated by this table over here, where if you use static word embedding for play using static embeddings like glove, you'll see the nearest neighbors all refer to some variations of play in a sports sense. Because if you think about it intuitively, when we're doing the glove embedding, we're just looking at word co-occurrences and whatnot. And obviously the word play, I think, co-occurs more with sports sense of the word than let's say theater orchestra. So that's why it's like with static word embeddings, you see the nearest neighbors. It is near to words that semantically means like physical sports. Whereas if you use Elmo embeddings, you can see that it was able to disambiguate between play word used in its context. So in the first example, you see that it was for a sports-specific reference, and the second one, it was with reference to an acting or a Broadway show. And they subsequently did ran the results on various downstream NLP tasks. At the time, these were some standard NLP benchmarks and the data sets. So you can see the task, and in red you can see what are the task acronyms represent, like textual entailment and semantic role labeling and so forth. And basically they show a significant increase in absolute and relative performance. All right, okay. Yeah, so yeah.
So can you explain when to use Elmo versus Glove?
Sorry?
Can you explain when to use Glove versus Elmo, like global vector?
Right. Okay. So for everyone, the question was when to use Glove versus Elmo. So I think if you can, you'd use Elmo or contextual embeddings all the time, right? Because first of all, it depends on whatever task you're trying to do, and in this case, you have to the contextual word vectors. So how do we evaluate the performance? So let's say, what is your downstream tasks? And if you can, you'd use contextual word embeddings because they show superior performance because they have better distributional semantic knowledge of the word token embedded in them. So if you use that as opposed to static word embeddings, the difference is the static word embeddings don't have that contextual information. So if you think about it, I cannot think of any task where you wouldn't want to have the contextual information. I guess that's interesting because I can think of something, okay? So we were doing this problem where we're trying to group words into different bins based on connections, and there was no context, right? So what is the contextual word embedding in that case? So in that case, what we found was that so in that case we found that using static embeddings actually gave better results because it had less noise. As opposed to contextual word embeddings. So it's interesting because I was going to answer to that question that, always use contextual word embeddings because they're superior, blah, 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 but that's not always the case. So to answer your question, yeah, it really depends on the task that you're trying to do. So for example, like if you have the task of, grouping 16 words into 4 groups, in that case, what would you use? And each of the word is by itself, right? There's no context. So if you use, let's say, an Elmo embedding or any other or BART trained embedding, in that case, that word would have meaning imposed on it, which we don't want to have, which we don't want it to have. We just want it to mean like a standalone word.
So just to summarize,
Yeah.
if context matters, then Elmo
I think that's a good way to look at it. And also remember that we talked about even the static vectors or the contextual word embeddings, the training corpus they're trained on. So that also matters, right? So, if it's, for example, if it's you're in a scenario you don't need any context, but if it's in the medical domain, I think it would be more superior to use embeddings that were trained on medical corpus as opposed to like, generic static embeddings. So it really depends on the problem that you're trying to solve and which domain and problem matters.
And the embeddings that are available, let's say, on phase, they come pre-trained, but you can still tune them, right?
So can you repeat the question?
Yeah, so the Elmo, like kind of like words embeddings, but they already come pre-trained, but you can like tune them based on another corpus.
Yes.
Is it the same with like Elmo, and is that kind of like the spirit that you have like some preset weights that come by default, and then you can add some like layer on top of that to like retrain on another corpus that it hasn't seen to tune it?
Yeah. So it is. You can fine tune the weights. So the question was that can you take some pre-trained weights and then fine tune it to your task? Now, when you're fine tuning, it depends on what is your objective when you're fine tuning, right? So if you just want to improve the embedding of the word in just a language modeling sense, then yes, you can fine tune. So let's say you take embedding and then you want to fine tune on medical words. So this is the paradigm that we see. We're going to discuss this in a few lectures after. But now, with the paradigm of like, alignment, language model alignment, first you do a supervised sort of fine tuning on the language modeling objective. What is the language modeling objective? You're given n words, and then you're trying to predict the next word, right? So let's say you take a medical corpus, and then you do a supervised fine tuning on the language modeling objective. So in that case, you're possibly improving the word embedding quality of based on that medical corpus, right? But let's say if you're fine tuning on a different objective, it's probably not going to improve the word embedding or language modeling. So the object, yes. So the answer is yes. Okay, so yeah, so I think today was a relatively short lecture, and the last thing I wanted to talk about is more of neural networks research, and the only thing I have to say is that it's an exciting time to be doing neural networks or deep learning research. However, because of the subject being very mainstream and with so much attention, mainstream attention on it, and literally almost every day there are hundreds of papers coming out, it's very important to retain our scientific skepticism and not get lost in the hype and focus on the scientific questions, true scientific questions. So today is a relatively short lecture. So we will start on neural machine translation next lecture. So if you have any questions, then I can open the floor.